Life has a rather interesting way of working things out sometimes and closing loops if you live long enough. In the summer of 1972, I returned to Duke University from a 2-year hitch on active duty in the Army, and I spent that first year back at Duke from the service in the research laboratory at Duke, a lab that I had inherited from Andy Wexler, who is the editor of our journal, of course, now. Andy was returning to the clinical program to finish his chief residency year. Andy had introduced the technique of using radioactive tracer microspheres to determine regional myocardial blood flow to Duke a year earlier, and I quickly learned 3 things. One was how to use microspheres. The second was that every paper that subsequently emanated from the lab had to have Andy's name on it. And the third, just joking, Andy, the third was that some guy named Gerald Buckberg at UCLA was the only other cardiac surgeon using microspheres in the same manner we were, and therefore, by definition, he was the competition. Well, in the fall of that year of 1972, just before the American College of Surgeons meeting in San Francisco, Dr. Sabiston called several of us together and said that a young surgeon from UCLA named Gerald Buckberg was about to present some extremely important and potentially earth-shaking work at the surgical forum there, showing that elective ventricular fibrillation was bad for the heart. Now, that'd be equivalent now approximately to saying that someone was about to tell us all that cardioplegia is bad for the heart, and maybe that's what this last paper was about, since almost everyone has used that for the last 25 or 30 years. Well, Dr. Buckberg's fellow, Dr. Chris Hottenrott, presented those papers. There were actually 2 of them, and it was indeed earth-shaking. The only problem was that we repeated the studies at Duke, got different results. That elicited a lot of correspondence between me and Dr. Buckberg over the next year or so, none of which was particularly laudatory and so on, and it culminated in my presentation of a paper a year or so later at the forum saying exactly the opposite, that ventricular fibrillation was in fact very safe in non-hypertrophied hearts. Well, following my 10-minute presentation of that paper, Dr. Buckberg had a rather hostile discussion that lasted 15 minutes. So thus began a series of several publications and counter-publications between our group at Duke and Dr. Buckberg's group at UCLA. But what started out as a rather intense rivalry from different sides of the different viewpoints gradually transformed into, well, maybe a modicum of respect, and then enormous respect, and then admiration, and ultimately it transformed into outright awe. Because over the past 3 decades, I've come to believe that Dr. Buckberg may well be the single most important person in our specialty during that time. His work in the field of myocardial preservation is now legendary. And as a direct result of his work in that field, I think it's probably correct to say that he saved more lives than any cardiac surgeon who's ever lived. Now, about 3 years ago, he approached me in an unusually excited state about a new concept he had of heart failure. He and Dr. Francisco Torrent Guas from Spain traveled to Washington, D.C. for a meeting to iron out some problems with their concept, which dealt with cardiac electrophysiology. Our first meeting ended with sort of a lingering atmosphere of skepticism, at least on my part, but with the realization that Gerald Buckberg was involved, I figured it was ultimately going to work out. During our subsequent meetings, the various concepts were ironed out and evolved into a beautiful, all-encompassing theory of cardiac anatomy and physiology. It also gave rise to several new surgical approaches, some of which have been discussed in this meeting already. Well, I was so impressed with the final concept that I asked Dr. Buckberg if he would consider giving my basic science lecture at this meeting of the American Association for Thoracic Surgery, and fortunately he accepted. Ironically, Dr. Buckberg will be only the second surgeon to ever give the basic science lecture at the American Association for Thoracic Surgery, and just so we can close the first loop, in case you're wondering who the first one was, it was Andrew Wexler. For this talk, I insisted on only one stipulation, that that he not present the information anywhere else, either in print or in presentation form, prior to this address. That was not an easy stipulation. With great restraint and self-control, he agreed to that stipulation, and as a result, you will hear today for the first time about this remarkable concept, a concept that I believe will ultimately be recognized as a unification concept of the heart. It's therefore with great pleasure that after almost 30 years I am totally closing the loop today by presenting to you a man whom I deeply admire and a friend who I deeply cherish, the 2001 Basic Science Lecturer of the American Association for Thoracic Surgery, Dr. Gerald D. Buckberg.
Thank you, Jim. It's a great privilege and a great honor to hear those wonderful remarks. I wish my parents were here, because my father probably would have thought he was in the wrong room, and my mother might have believed you. But I would like to share with you something we've thought about, and it's an enormous privilege and honor to be allowed to give the Basic Science Lecture. And the title that I've selected is The Helix in the Heart. I'd like to take you with me on an adventure that I've taken over the last 3 years. And I described this to my children many years ago as discovery, and that is, you can walk down certain pathways that are common, but you have to see something different as you walk along. And what I'll talk with you about is my concept of how the helix in the heart affects nature, the heart, and the human. Now, this is a voyage into something that I have not seen before. And I selected a comment from my hero, Albert Einstein, who said that all of our science measured against reality is primitive and childlike, and yet is the most precious thing we have. So we all have to be students. And basically, a student is often wrong and always in doubt. Professor is sometimes wrong and never in doubt. So please join me on my student pathway to see something that I've just discovered recently, and I'll share with you. Now, the object of our affection, of course, is the heart. And as you can look at the heart, it is really a helix. And as you look closer at the heart at the apex, you'll find that that helix was described in the 1660s by Lauer as having a vortex. And the vortex fibers go from outside in a clockwise way, and from inside out in a counterclockwise way. Now, that combination of clockwise and counterclockwise vortices is common in nature. For example, if you look at a flower bud of a daisy, you'll see the same clockwise and counterclockwise spirals. But you'll also note that the buds of the daisy increase in size as they go from the center and outward. And as you look at that increase in size of these clockwise and counterclockwise spirals and put a radial line across that, you'll find that is the natural pattern of growth. And as we look in nature, you'll find many pathways of clockwise and counterclockwise spirals as if they're reciprocal spirals. Now, as we look at reciprocal spirals, we'll see they are common in nature. For example, if you look at a shell, you can see a shell has a clockwise and a counterclockwise pattern. If you take the tip of that shell and draw it outward, you'll find the tip of that shell forms a helix. And that helix is very much like what we see in the heart. As you look at these helices, you'll find they're common in many animals. For example, a ram-like animal like an eland, who has clockwise and counterclockwise spirals in their horns. Yet if these horns counteracted one another in combat, they do not break, because nature has another little trick. It produces spirals within spirals. That is a way of supporting one structure from another. And in a sense, nature has a harmony of structures one to another, both outside and inside. As we look at that harmony, we can go back many years to Pythagoras in 600 BC, who talked about the golden section. The small is to the large, as the largest in the whole. However, in nature, there is a symphony of harmonies between different parts. This was described by Fabinici from Leonardo at Pisa in 1250. And he talked about this concept of harmony between parts, or a symphony, resembling a logarithmic spiral. And as we look in nature, we see logarithmic spirals going in different directions. Perhaps one we know best is the logarithmic spiral of DNA, a double helix holding the sugar and phosphate ions, or parts that are the blueprint of the master plan of life. And we go from DNA upward, and we find that we see a spiral galaxy 37 million light miles away that shows the same spiral formation. But let's return a second to the human. As we look at a human, we find we all have counterclockwise and clockwise spirals. If you look at our fingertips, we are similar in harmony, yet we have some differences. And that harmonic part we see in our fingertip also goes to our heart, where we have the clockwise and counterclockwise spirals of the apex. This is taken from a picture from Pettigrew in 1864. And we've looked at the heart as surgeons in anatomy, looking at internal and external spiral loops, or bulbal spiral and sinospiral loops, with a little pathway around the heart, which I'll talk to you about in just a moment. As we look from the bottom of the heart upward, we see the same clockwise and counterclockwise spiral formation. We then look at the apex. The apex, but from outside and within, has the same spiral formation. Now, these sections of the heart were obtained by Dr. Terence Guasp, who put these pictures in the Handbook of Physiology. And the problem that's existed for many years in anatomy has been called the Gordian knot of anatomy. Anatomists have dissected the heart for many years, but yet they didn't understand where the heart started and where the heart stopped. And this has been a potential problem forever. And Dr. Guasp has solved this mystery by showing the origin and end of the heart myocardial fiber band. And he said this really looked like a rope. And I thought that was a little peculiar when I heard it, but it really has three parts. It has a beginning and an end at the aorta and pulmonary artery, a wraparound loop called a basal loop, and then a helix. And I said, where did you get the idea that the heart really looked like a rope? And he said, well, I went back to phylogeny. And I looked at a worm that's 1 billion years old. And a worm really is like a rope with a venous and an arterial system. At 400 million years ago, we went to a fish with the first generation of a heart with gills in the system. 200 million years ago, we went to an amphibia and a reptile, in which we have an atrium and a ventricle separated by atrial defect and a ventricular defect. And about 100,000 years ago, we went to man, in which we have the heart where the atrial defect is closed and the ventricular defect is closed. So I said, let me look at this a little more carefully. So I went to Netter's Book of Anatomy, and I found, as we looked at 20 days of life, the heart of a person looked like a worm 1 billion years ago. At 25 days of life, we have a venous system and an arterial system, and in a sense, we mirror at 25 days what a fish looked like 400 million years ago. At 30 days, we look at the heart, we see a patent ventricular septal defect and an atrial septal defect, and we mirror the amphibia and the reptile. And finally, at 50 days of life, we have an intact atrial septum and an intact ventricular septum. So in one sense, in 50 days of life, our evolution encompasses 1 billion years of history. I find that's quite remarkable. But yet the next question comes up, how can this ventricle really reflect the heart? And so we'll now look at the rope we saw below, and we'll look at the heart above. And we'll see a relationship between the rope and the heart. Remember, I said there are three components, a beginning and an end, a surrounding basal loop, and a helix. As one dissects the heart out, you find you remove the aorta from the pulmonary artery. And as you do this, you unfold the right ventricular free wall, which is transverse, and the helical apex. The next step is to show that this wrap surrounds both ventricles, which is done. The next step is to unfold the helix of the heart, to unroof the aorta from the ascending and descending limbs of this helix. This is done by unwrapping the coil, and when the coil is unwrapped, you have a flat myocardial band and a flat rope. Well, this looks a little bit like it maybe something is in a cartoon. So the next step I'd like to propose to you or show you is how this happens as one dissects out the heart. Can I have that first video, please? You see the heart in front of you, the pulmonary artery and the aorta, the right and left ventricle and septum. And this entire dissection will be done with the hands. There are no instruments. The first step is to remove the pulmonary artery from the aorta. Once that is done, the dissection goes along the ventricular septum to free the free wall of the right ventricle. As you can see, the free wall of the right ventricle is now freed or opened. Then the band of the ventricle goes around the ventricle to surround the ventricle as if it's a buttress. And using natural cleavage planes, you'll see that that buttress is removed from the back wall of the septum and the left ventricle. You can see the normal cleavage planes that are dissected by Dr. Guasp doing this dissection. When he's finished, you have the free wall of the right ventricle. You then have a genu between the right and left ventricular part of this wraparound basal loop that surrounds the ventricle in a transverse way. The next step is to unroof the aorta. You can see how this band moves into the ventricle to form a transverse band, and then it goes into the ventricle to basically form a helix that goes into the ventricular muscle fiber. He then unroofs the aorta by removing the trigones, the left and the right. At that point, he unfolds the ventricle. And with this unfolding, you'll see that he separates the ascending and descending parts of the helix to uncoil the helix. You can see the natural cleavage planes. Once the helix is uncoiled, the heart has been completely dissected, the aorta and the pulmonary artery. By simply continuing the unwrap of that loop, you'll find that the intact myocardium becomes a single muscle band from aorta to pulmonary artery on the other side. The next step is to refold the ventricle with a fold in the middle that allows the transverse and apical loops to occur. He then recoils the helix, dropping down the ascending segment and then reforming the coil in the ventricle. Pulmonary artery here, aorta here, descending loop. By reattaching the aorta to the descending segment, called the feet of the aorta, you have a heart, the left ventricle and septum, and a free wall of the right ventricle. The next step is simply refold the ventricle. And with that, the muscular band becomes an intact heart. Now, as you see this, you might think this is really a dissection done by a certain individual and may not be real. And there's a fascinating study that was done by Dr. Lunkenheimer in Germany, in which he put a catheter in the aorta and injected air into the aorta to cause dissection of the coronary arteries without dissection of the heart at all. That is, an air dissection such as emphysema, and then did a CAT scan of the ventricle to look at the parts of the ventricle. This is called a transpneumonic spreading of the myocardial network. And what we've done now is put a catheter in the aorta and injected air to dissect along the coronary arteries, and suddenly there's a tremendous dissection and a blow up of the heart at 60 millimeters of mercury pressure. When he blows the heart up like this, he's changed the architecture. And now you'll see the internal spiral formations of the ventricle without dissection. You can see the clockwise spiral on the inside and the counterclockwise spiral on the outside. And we're moving now from the base of the heart to the apex. As we go from the apex to the base with no dissection, you again see the counterclockwise and clockwise spirals. Here's the right ventricle. Each spiral maintains its own integrity and contributes to the whole. As you look at these spirals moving in different directions, you see this is a dead heart, but you're looking at the anatomic structure of an uneven spiral network that goes from one spiral to another. So now we have definition of this not only by dissection, but also definition by another form of approach to look at the spiral geometry of the ventricle. Now, the next step we have to do is see if this form of the ventricle has reality in terms of function. Can we see the dissection going along this myocardial band? And we do this with a MUGA scan, with a multi-gated imagery, that we can see the sequential contraction of the ventricle. And this is done to show that the heart really has peristalsis along this muscular fold. Now, this is an intact ventricle in diastole. This is the basal loop, and this is the apical loop. The first thing that happens is you have contraction of the descending segment. I should say of the right part of the basal loop. That contraction goes around the basal loop to the left side of the basal loop. As that contraction progresses over time, it goes down the descending segment and moves around the apex and goes up the ascending segment. And following contraction of the basal loop and ascending loop, or I should say in the apical loop, the heart relaxes in diastole. So now we have a sequence of morphology, sequence of contraction. Let's see how this works in terms of function. Well, we've looked at the heart for many years, and this again is the basal loop and the apical loop. And normally, we think of the heart as contracting and relaxing, constricting and dilating. We learned this, can you go back one slide, please? We learned this from William Harvey. In reality, the predominant motion of the heart is not just that, but it's shortening and narrowing. As we see the contraction of the basal loop, we see a squeeze of the ventricle, a stiff outer shell in the ventricle to allow this part of the ventricle to function. The next step is that there's a twist down of the muscle fibers to allow the heart to eject. This twisting is reported by Borelli many years ago, like wringing a rag. The next step is that contraction goes up the ascending segment for it to lengthen. Can you go back one, please? No, it went too fast. Keep going. Can you keep going? It took up. No, just keep going forward. Let me just push this. We'll get into contraction in a second. Here we go. Twisting down, twisting upward, and relaxing in diastole. Now, I'd like to show you how this works, not only in this cartoon, but show you how this works in life. That is, the way the heart works is it twists to eject and twists in other ways. You'll see the clockwise and counterclockwise twisting of the ventricle as we see it in the operating room. We'll also see how this works on an MRI scan. Can you shot the next movie, please? This is the ventricle as we see it in the operating room, with the tip of the apex sitting like this. The natural twisting and untwisting of the heart in different directions. As you look at an MRI, you see the apex does not move. The predominant action is shortening and lengthening. Shortening and lengthening. And with the shortening and lengthening, there's ejection and suction to fill. Ejection and suction to fill. So this is the normal activity of the heart. So let me see if I can correlate this activity in terms of how we relate both the structure of the heart, the MRI, and the function as we see it in the operating room and the cath lab. We start out with a heart in diastole with passive filling. The next thing that happens is there's constriction of the basal loop. There's a stiff outer shell around the ventricle. And that's responsible for the isovolumetric phase of systole, when the mitral valve narrows. The next step is the descending loop twisting down to eject. When that twists down to eject, you have the ejection phase, where the heart basically forms thickening rather than narrowing as we thought before. With that thickening is ejection to the aorta. That systole extends into the contraction of the helix around the descending segment up into the ascending segment. As we go up the ascending segment, you see isovolumetric lengthening of the heart. But the mitral and tricuspid valves are closed. In a sense, what happens is the heart increases its size without changing its volume. And it creates an avenue for suction. And as soon as the aortic pressure, ventricular pressure goes below the atrial pressure, the heart sucks to achieve venous return, all of which occurs in systole. And only then does the heart relax in diastole for filling. And so we see something that's very interesting. We see a circumstance in which we understand completely how a heart can contract and shorten. But how can a heart contract and lengthen? Well, we borrow some more little tricks from nature. You see the transverse basal loop here and the helix over here. If you look at a snake or look at one of the eels we saw last night, we'll find that as they move, they shorten, and the snake shortens and gets higher and higher. And fundamentally, if you look at this basal loop as a spiral, I should say the apical loop is a spiral seen here. With the beginning of systole, you have a counterclockwise and clockwise twist of the ventricle. Much is described by Borelli of the heart back in the year 1680 to eject. What Dr. Guasp has shown us is the heart also has a second part of this coil, which is the ascending segment. As the blood goes around the ascending segment, it twists clockwise and counterclockwise in a separate direction. And even though the fibers get thicker and shorter, these fibers have been lengthened because they weren't contracting. You see the heart gets longer at that time. And by getting longer at that time, you see that the heart will lengthen. The snake is not a very good way of looking at this because the snake is longitudinal. We can then borrow another trick from nature. That's the trick I showed you before about the spiral within spirals. The reason these ram's horns did not break when they made contact. Because in a sense, you'll see that this is the twist of the heart. And if you put the spiral in these muscles, you'll see the spiral goes down as if you're twisting a coil in different directions to eject, and then twisting a coil in an opposite direction to lengthen. But the intriguing thing about this diagram is that we have a spiral formation, but these coils are of different lengths. As you look at the coils of different length, you'll say, here is the helical heart, the spiral formation. It conforms very nicely to the mathematical description of spiral ejection. But these spirals have different lengths. And as you look at the heart and separate the ascending segment from the descending segment, you'll find that they have a harmony of length. And the harmony of length between the descending and ascending segment of the basal loop conforms precisely to what Pythagoras talked about with the golden section, of the small to the large and the large to the whole. I find this is absolutely a fascinating miracle to me. I'm in awe of how the heart really works. And in a sense, the heart has a remarkable hidden harmony of spirals. And that hidden harmony starts with the master plan of DNA, a double helix that tells us a direction. It moves from DNA to the spiral we can see as we look at the outside of the heart when we dissect it. But that spiral on the outside of the heart of a dead heart also has to come to life. And when it comes to life, you'll find the spirals beat in different directions to clockwise and counterclockwise twist, both to eject and to suck. As we looked at this ejection and suction, we find it borrows another little trick from nature. And that trick from nature is we have a coil within a coil for clockwise and counterclockwise rotation and activity. But as we think of the activity of the heart, we think of actin, myosin, and calcium. As we look at myosin, myosin is a double helix. It goes through ATP into the thin filament of actin, which is a double helix. It moves then to tropomyosin, which is a double helix. Then it goes into calcium. And as one looks at calcium with confocal microscopy, this is an individual myocardial cell. You could see there's a calcium spiral within the heart. As if even in the individual cell you see this calcium moving down the spiral. If you look at the individual calcium ions, you'll find another spiral of the calcium that's in red. So in a sense, there's a symphony of form within the heart, and the spiral perhaps are the keys to the kingdom. In the kingdom we see are gargantuan relatives, from ionic to cosmic. Now, of course, the next question you'd ask is why a surgeon wants to know all about this anatomy and physiology, when our job is to really look at structure and function. Well, structure and function relates to what we do every day. And as we know, we've looked at congestive heart failure, which is a leading cause of death in this country. And leading cause of death occurs because the helix has been destroyed. That is, instead of a normal helical or elliptical formation of the heart, we basically have a sphere. As we look at that sphere, we have to understand this better in terms of this anatomy. Can I have that next video, please? This is a normal heart showing ejection and suction, as I talked about before, with a normal apical ellipse as shown by Dr. Suma yesterday. This is heart failure, a big dilated ventricle, which lost the shortening and lengthening, and with dilatation we see mitral insufficiency. So we're looking at a change in the form of the heart that also will affect its function. Now, let's look at that function again in terms of the helix. Here is the normal heart that has a 15% fiber shortening. But there's a relationship between fiber shortening and fiber angulation. If the heart is made in a spiral formation, you'll find that the fiber shortening results in a 60% ejection fraction. Conversely, if the fiber orientation is transverse, as occurs in the basal loop, there's only a 30% ejection fraction. So here are the hearts we see in heart failure. We see an ischemic heart with a lost apex. We see a dilated heart in which there's valvular insufficiency from volume. Or we see a non-ischemic heart in which the muscle itself has been damaged. And the question we have to ask is how this anatomy can help us understand this heart and how it functions. Well, this is the normal ventricle as you see here, with the basal loop and the helical apical loop. In the second part of this diagram, I've separated the basal loop from the apical loop to look at the orientation of fibers. With heart failure, you lose the apex. You form a sphere. It's separated here. In a sense, what heart failure is to make the apical loop, I should say, to make the apical loop more basal. That is, you make these fibers transverse rather than oblique. Here's the oblique orientation with a 60% ejection fraction, and here's the more transverse orientation with only a 30% ejection fraction if the fibers are normal. Now, in a sense, what we're doing is a heart that's damaged is like a basketball. A heart that's normal is a football. Of course, you throw it, it's a spiral. And the objective in dealing with heart failure is to change the basketball back into a football. Well, here's the spherical ventricle, and here's ischemic cardiomyopathy. And Connie Athanasiliou told you yesterday about some of the work we did that mirrored the work done by Vincent Dorr. We take this abnormal segment that's injured and we open it in the operating room. We place a stitch around the junction between the contracting and non-contracting regions that have been shown us so nicely by Dr. Fontan. We bring this stitch together to form a surgical neck or an apex. We then take a patch and put a patch over that segment of the apex. We put the patch into place and we close the muscle. So we've taken advantage of this sphere and made the heart more elliptical. We also can take advantage of some of the things that Paco told us about before, and we designed this operation we call apocopexy. Here's a dilated heart, and Dr. Suma talked about this yesterday. A sphere with the same incision. The ventricle is opened. A stitch is made, or individual sutures made along the septum. These are brought together to form more of a cone, I should say. A patch is placed now from the papillary muscle below to below the aorta above. And when that patch is placed, you converted that sphere into an elliptical form. And as this muscle is closed over the ventricle, if it's done in an imbricating way, we may have returned the ventricle to a more apical configuration. Now, I think we may have found a solution surgically by understanding nature more carefully. In ischemic disease, we take the dilated heart and try to make it into an ellipse. With a dilated cardiomyopathy, we've noticed from Dr. Sumi yesterday, this muscle can be damaged, and we can exclude it and make a more elliptical formation. And it's possible that we may in the future deal with valvular cardiomyopathy. We learned from Dr. Lytle and Dr. Serrano about a 70% mortality in 10 years after valve replacement, perhaps because you haven't changed the ventricle. It may be possible when this muscle is more normal to do exactly the same operation in patients with dilated hearts and valve disease and change not only the heart but the ventricle. Now, the next question, of course, is does this formation of an apex in a heart relate only to biology? Well, I'm not sure. It also relates into structure in terms of architecture. This is a Greek temple. You can see they have pillars, and they have a base up here. And with the base, you have to have the pillars close together to hold that basal structure. And only one person can walk between those pillars, or the beam, I should say, which is the upper structure. If you move from the temple you see here to what the Romans have contributed, they changed the anatomy a little bit, and they made the semicircle. The semicircle has a keystone on top, and more people can walk through this. But in order to make this higher, you have to make it wider. So you're stuck with this design. In a sense, this design is a little bit the design of a heart that's in heart failure. What we want to do is make an apex. Well, if we make an apex, you can see this is a hut seen by Indians or Celtic huts. Here's the apex. But the forces now go downward, and they're supported by a buttress. If you want to take more people from the hut and bring them in under an area, you see more people can enter, and now you put an internal buttress with the same apex. If you move further and get more people into that area, you'll find that the Gothic dome is seen here with an external buttress. If you want to make that even bigger, you make a cathedral with a Gothic dome and an external buttress. And so we see this change in architecture which follows a change in anatomy. And the question is, did God first make a church, or did he make a heart? Here's the apex, and here's the buttress of the basal loop. Was this anatomy that God found a unique form related to the heart? Or did he look at the glacial age? This is an iceberg, and this is the ventricle. They look pretty similar. I got this drawing from Delta Airlines. It's called, in a section called Imagination. And basically, imagination is interesting, and I read something many years ago by Egon Schiele, an artist. He said, a painter can make you look, but to see is something special. And I think we can see certain relationships here. But these are structures that are not alive. What happens when we bring life into these structures? The heart, as you know, has an apex, and has a cone to an apex to provide a vortex. And that vortex is what makes the muscle work. The tip of that vortex doesn't seem to move, but it really is the motor of the ventricle. And that motor of the ventricle, which is the tip, may essentially be the eye of a hurricane. And this is a vortex of a large hurricane affecting Bangladesh. Or that hurricane can go in a different direction and then go into the nebula of heaven. And we see the same anatomy, the same change in form. And so that led me to ask a question about nature and creation. And I learned this by reading a little bit of Leonardo da Vinci. And da Vinci said that nature can be fixed, but man can be infinite because it can have the hand and the mind and the eye, and they can coordinate. And that coordination makes creation so we can begin to see the relationships between parts. I learned some of this by meeting with Dr. Francisco Torrent Guasp, and he opened my eyes to a new way of looking at the ventricle 3 years ago. He discovered this as a student about 50 years ago when he was in Madrid, and he described this in a book that is not published in the United States, but he gave me a copy of this, and he's written about this. When he did that, he looked at the same vortical formation of the apex we talked about a little bit ago. He also looked at the apex in another way, as you can see here, at the vortex again. And when he described the motion of muscle on either direction through that apex, he described exactly the same clockwise and counterclockwise rotation we saw a few moments ago. Did he see this in the heart? Or did he look at a pine cone to see how that worked? Because if you look at a pine cone, you'll see that the orientation of fibers in a pine cone have exactly the same clockwise and counterclockwise rotation seen in the pine cone as we saw in the daisy a little bit ago. So Dr. Gwas said something very interesting to me. He said, Gerald, he says, nature is simple, but scientists are complicated. And as he said this, I said, well, how did you understand about the fact the heart sucked in diastole? He said, I went back and read about Erasistratus, who lived 2,300 years ago, who thought that blood had blood and air in it because he couldn't understand how the blue blood got red. But he said the heart sucked in diastole. And it's interesting that Erasistratus was the first arrhythmologist. And here he's seeing Antiochus, who's the son of the king, who developed palpitations when he saw the king's wife. And Erasistratus diagnosed this, told the king about this. The king divorced his wife, and the arrhythmias went away. So, Jim, are your arrhythmias having a legal bent from the past? He then looked at Galen. And Galen was the doctor of the gladiators. And he looked inside the chest of people that were injured, and he saw the heart sucking in diastole. And Galen changed what Erasistratus said and had blood really had blood. And it wasn't just blood and air. And everybody believed what Galen said about the to and fro motion of the heart until Harvey came along in 1638. And Harvey wrote the classic book, The Anatomic Exercises of William Harvey. And when he wrote the book of The Anatomic Exercises of William Harvey, it was an enormous breakthrough in science. It was Harvey's breakthrough that stunned his colleagues, that still clung to the theories of Aristotle and Galen and others. Theories Harvey proved both inadequate and inaccurate. And this was the first English translation. They said that Harvey contradicted Berzelius, who fitted anatomy to the glennical system. That is the ebb and flow concept. If you look at the waves in the ocean, it's exactly how the heart works. But Harvey said the heart did not dilate and take the shape of a cupping glass and suck blood into it. I think it tells us something very interesting, that our leaders can be wonderful, but they're not perfect, because the heart does indeed suck. So I went back a little further, and I looked at the work of Andreas Berzelius. And Berzelius is the father of anatomy. And as the father of anatomy, he dissected hearts. And as you see his dissections appearing in the 1500s, you can see the transverse section of the myocardium. And as he described this dissection in his book, he said the earliest example since Leonardo da Vinci showing the thickness of the walls and shape of the ventricular cavity. So this was in the 1500s. So I went back and got a book of Leonardo da Vinci's. And I looked through his anatomic sections, and I can see that da Vinci had an anatomic section in which he showed also the transverse section of the heart that you can see. And da Vinci said that the apex, or tip of the heart, comprises the left ventricles. He understood the apex was very important. But da Vinci was also fascinated with vortices. And I think we've learned a lot about da Vinci's concepts and vortices by listening to Dr. Robichek, who's told us about his unique designs. And da Vinci saw the clockwise and counterclockwise spirals within the aorta. And of course, you'd have to say, did da Vinci discover the way that the blood flowed through the aorta? Did he look back at a Greek temple 500 years before BC to see the same clockwise and counterclockwise spirals? Did he look further back to Neolithic times in 5,000 years BC when people would draw on graves these clockwise and counterclockwise spirals? Or he looked back 400 million years ago to a fish that has the same clockwise and counterclockwise spirals. This study was taken from Maury Grebe, you'll hear about in a few moments. This is the size of a human hair. This is the heart. This is the aorta. This heart has 5 cells thick in it. And you'll see it has the same clockwise and counterclockwise spirals. And as you make the heart beat, you can see it has a normal ejection fraction and has the same spiral formation in the aorta. You can see the red cells, one at a time, going through the gills. Did we look at something 400 million years ago that was a little bit less than the size of a hair? Or did we go in a different direction and look upward at the cosmic waltz of two clockwise and counterclockwise spirals that are basically 5.9 thousand trillion miles wide? It's all the same pattern. And so I'll conclude by looking back at being and becoming and return to my hero, who's Albert Einstein, who said something very interesting about general relativity, because he understood the concept of equivalence and proportionality. He said, matter tells space how to bend, and space tells matter how to move. As you look at his concept, you'll see that matter, which is the sun, pushes on time-space like pushing on a rubber band. You notice the way that push occurs, it occurs in an elliptical fashion. If you push really hard on that time-space, you'll find you have a hole that becomes a spiral. And that spiral is very interesting because it goes downward and upward. And Einstein said that God did not play dice, but didn't take chances. Is it possible the concept of going downward and upward in space is similar to ejection and suction in the heart? Are they really the same thing? When you think about how suction started, it started many years ago and it changed, but it changed back again. So you go back to Galen. Galen said something very interesting. He said the overlying heart at each diastole robs the vena cava by violence of a considerable quantity of blood. So he's describing this violent suction of blood back looking inside the chest of an animal, of a gladiator that was injured with a chest wound. But he also was taught by someone, and he was taught by Erasistratus. They asked him what he thought about Erasistratus. He said he had plenty to say in his early career, but now, like a slave with excessive rascality, when caught in the act of thieving, he hides the missing article and denies seeing it. So he didn't like Erasistratus very well at all. But he liked someone worse, and that was Lycus of Macedonia. He said he was the worst doctrine of all. He spoke as if he started from inner sanctuary. And when he asked to describe Lycus of Macedonia, he said he really wasn't as good as any of the other wonderful Greeks that he knew about before. He neither spoke good Erasistraticism or Hippocratism. He described him like a white crow who doesn't mix with genuine crows owing to color, nor with pigeons owing to size. But then he said perhaps the most wonderful statement made in the concept of learning. He said that Lycus of Macedonia is not to be disregarded, because he may perhaps state some wonderful truth unknown to any of his predecessors, which means no matter how much we like or dislike someone, we always must listen to them to learn. Because as we do that, we begin to see a very interesting thought of mine, which is ignorance is being unknowledgeable but can learn. Arrogance is knowledgeable but unable to be taught. And I think we have to maintain our student ways, because if we do this, we begin to enter what I think is the spiral of learning. And that is, if we enter into this spiral again, we see as we learn more, we go down this loop and increase our concept of knowledge. But as we get knowledge, we can move back up in a different direction and grasp those concepts and have wisdom. And in a sense, growth is knowledge which to analyze, differentiate, or take things apart. Wisdom is to synthesize, integrate, put things together, to see with the eyes of the mind. But these are not very helpful unless we have one other action, which is wholeness. That is, to bring together diversities, to have complementary activity. And I think we as cardiac surgeons are particularly fortunate because we can learn, we can understand, and we can act on the part of our patients. So I'll conclude with one more statement from Albert Einstein, who said that there exists a passion for comprehension just as there exists a passion for music. That passion is rather common in children, but gets lost in most people later on. I hope not. Thank you.